finishing up 17.7, surface integrals of vector fields. Okay. So in order to talk about this sort of thing, we're actually going to need to define something called an oriented surface. Okay. So now the definition is not really a good one, but this is it. So if it is possible to choose a unit normal n at each point of a surface S in a continuous way. Then one we call S an oriented surface. We call S an oriented surface, and we call the choice of n the orientation. Okay. So being orientable basically means that there's a consistent way of choosing. There's a smooth way of choosing a normal vector to it. Okay. Now that would seem sort of mysterious. What does that mean? Let me try and give you an example. So let's look at, if we look at this plane, okay, here's a plane P. Okay. Now you can choose unit normals on this plane, to this plane, right? So you think of this plane as sitting in R3, right? And at each point we can choose unit normals, right? All these things are unit normals, right? And we could make it so that at every point we choose the upwards unit normal. Okay, that's right. That's one way. And so you say, okay, look, we can choose a unit normal at each point of the surface in a continuous way, right? As we move around, these unit normals don't suddenly do crazy things, right? It's very like to every point you're always getting, the unit normal is not really changing that much. Okay. So there's a continuous way of doing it, and so this thing is the plane is an orientable surface, and we've got the upwards normal orientation. Okay. Now, if we had chosen our unit normals to be more random, suppose at every point we flip a coin and we say if it's heads it's up, if it's tails it's down. Okay. Then that would be a choice of unit normal, but it would be a discontinuous one, right? Because as we move a little bit, it suddenly goes down, right? We move a little bit more, it suddenly goes back up again, right? So the flipping is very discontinuous. Okay, so however, for the plane, there is a way to do it in a continuous way, and so this is an orientable surface. Okay. Now, if I have something like the Mobius strip, right? Are you all familiar with a Mobius strip? Anyone know what a Mobius strip is? No? Okay. So Mobius strip is something cool. You take a sheet of paper, and take a strip off of it. you take a strip of paper, and so if I go like this and make like a make this loop, okay, that's one way of doing it, and you see that I could choose unit normals. I could choose unit normals like this, right? Like always going outside, right? And so this is still considered an orientable surface, right? This is an orientable surface. Or I could have chosen them going inside. That would have also been continuous, right? You move a little bit, and maybe your unit normal changes a little bit, but it doesn't drastically change, right? Okay. Now, if you take a sheet of paper and you put a half twist, you twist it halfway and then bring it back together. Okay. Now this thing is called a Mobius strip. Okay. And what's funny about the Mobius strip is that it has only one side. Okay. It has only one side because if I'm here and I'm saying, okay, this is the front, right? So I'm drawing on the front of it. I come back, boom, but I end up at the same place I started, and I cover both sides. I end up covering the whole thing. Okay, so if you draw on the Mobius strip, you find that it looks like it has two sides, but actually it's a one-sided thing. Okay, so if you now think of what would happen if you tried to associate a normal to this guy, a unit normal at every point. Well, I want my unit normal not to change that much, right? So I'm going to choose it like this. But when you come back, you find that your unit normal is upside down, right? Because it's on the other side, right? So I'm sorry. When you come back to here, you find that you're actually on the other side. And so what happens is that your choice of unit normal, you can't choose a unit normal in a continuous way for this surface. Okay, so this is what's called a non-orientable surface. Okay, yeah. So yeah. So yeah. So basically, I guess the way you want to think of it is that for us, if we're talking about surfaces, then an orientable surface. So basically, orientable is the same thing as something like two-sided. Okay. Basically like two-sided. And we remark that some surfaces are not orientable. For example, the Mobius strip. Another way of thinking about the Mobius strip is like this: if I were on the Mobius strip, okay. So pretend that I've twisted this side and brought it back to here. Okay. If I were somebody living on the Mobius strip, so this is A square. I don't know if you've read the book called. I don't know if have any of you seen the book Flatland? Read the book Flatland? You've seen the movie? Oh, okay, yeah. So the story is about this two-dimensional guy who lives on a plane. His name is A square. A square. And he's visited by a three-dimensional sphere. So this three-dimensional sphere, shows up and passes. Initially, shows up as a point. But as he passes through the plane, he shows up he basically shows up as a point that becomes a circle that increases to large size and then decreases back down to a point again, right? So the sphere visits him and introduces him to the third dimension, basically. It's a pretty cool story. So if A square were living on a Mobius strip, then what would happen as he went here and passed through here, he'd get flipped over, right? So he'd look like this, right? And then he'd come back, he'd come back and meet all his friends, but all of his friends would say, "What happened to you?" Right? Because when he came back, let's see what happens. When he came back to see them, right, he would look like this, but if he let him spin, and he would have turned into a left-facing guy, right? Maybe everybody else in the square, in the flatland world is right-facing, right? But this guy who traveled all the way around their world would come back and he'd be reversed. Okay, and so this is what we mean by a non-orientable surface, right? There's no the orientation gets messed up. Is not preserved. Okay. Okay. Yeah. So, for example, you could have like a three-dimensional analog of the Mobius strip, and if I happen to pass through that thing and come back through the loop, then I would come back left-handed, right? Or basically. I think much worse things might happen. Okay. Okay. So orientable surfaces. There's some conventions about them. First, if S is a graph of a function, then we choose n to be the upward normal. So we're always, whenever we have a graph, right, you have something like this. Whenever you have the graph of something, we're always going to choose the unit normal to be the upwards pointing normal. Okay. 2, if S is given as a parametrized surface, then we're always going to choose n to be Ru cross UV, Ru cross RV over the magnitude of that. Okay. So we're always going to take the cross product of the derivative with respect to the first variable against the derivative with respect to the second variable. Okay. Number 3, for S, a closed surface, we're always going to choose n to be the outward normal vector. Okay, rather than an inward. So if we have like a sphere, then the unit normal we choose, the orientation we choose will be the one where the normal vectors are pointing out. So here's the as long as if we have an oriented surface, then we can make the following definition. So this is the surface integral of a vector field on a surface. So you have S, an oriented surface with normal n, and F, a continuous vector field on S. Then we define the integral of the vector field on the surface we define as the integral of this function the function you get by taking the dot product of f against the unit normal. Okay, so again, we're making a definition that we define in terms of this other definition, just like we did with the line integrals, right? We define the unit integral, the integral of the vector field along a curve by taking the field against the unit tangent vector, right, and integrating that function. Okay, so let's decode the notation. Let's decode the notation. Right, decoding the notation. What's this thing here? F dot n ds s. Right. Let's say that s is parametrized by r, some function r. So let's just decode what this means, right? What is this? What is this? Remember, this is the surface integral of this function, right? So what do we get? It's going to be the double integral over d of the function, and then times the magnitude of u du dv, right? Now, what's this thing here? F dot n. N is this, right? N is this. So let's write it out. F at r u v dotted against n, right? N is Ru cross UV, RV, over magnitude of Ru cross RV, right? And we multiply that by Ru cross UV's magnitude du dv over d. Right? And so in terms of calculating it, what you end up with is f of r uv dotted against ru cross rv du dv. So here's this thing. Here's the definition, right? The integral of a vector field on a surface is defined to be this, and then using what we did last, just decoding what this definition is, what the integral of this function is, you work it out and you see that you get this integral. Okay. So. So, for example, somebody asks you to calculate the flux of the field through this surface. So, where the field is y, x, z. So xyz gets turned into yxz, and S is the paraboloid. Z equals 1 minus x squared minus y squared over the unit circle, the unit disk, x squared plus y squared is less than or equal to 1. These things are also called flux integrals. You measure the flow of the field through the surface. Okay. Just to come back here for a second, right? Here you have the surface S, right? Here you have the surface S, and you see what you're doing, right? You're taking this field, right? At every point you have some vector, right? So you have like particles, and the field maybe denotes the velocity of each particle at that point. Okay. And what you do is you take the dot product of that against the unit normal, right? So the unit normal is this way, are these guys. Right? These guys are the unit normals, and you take the dot product against it, right? And so this basically measures how much of the field is flowing in the direction of the unit normal, right? And then you take the sum of all those things, and that's the flux of the field through, through the surface. Well, okay. Okay, is everyone all right? Any questions? Any questions? Sydney?
No.
Any question? No?
I was not good.
Okay. So, So we want to calculate this thing. Let's take a parametrization. R of xy is xy 1 minus x squared minus y squared. R sub x is going to be 1, 0, negative 2x. R sub y is going to be 0, 1, negative 2y. Cross product is going to be negative 2x. I'm sorry, positive 2x, and then negative 2y, and then 1. Right, 2x, 2y, 1. Okay. And then the magnitude of that is the square root of 1 plus 4x squared plus 4y squared. Okay. Right. Picture is you have you have a downwards paraboloid, right? You have a downwards paraboloid. Sorry, my stomach is growling. You have this downward paraboloid, right? And here you see that we've got 2x, 2 for each point xy, right? For each point xy, we have this thing 2x, 2y, comma 1. Right? So 2x, 2y. So it's going to be 2x, 2y, comma 1. So this guy's going opposite like this. Okay. So So then, what's this going to be? When we calculate the integral, right? So this is going to turn out to be the integral over the disk of f evaluated at RUV dotted against 2x, 2y, 1 dA. Oops, I should probably use x's and y's. R, x, y. Dotted against that. Right. R, x, y is xy, 1 minus x squared minus y squared. And so this thing here is going to be y, x, 1 minus x squared minus y squared. Right? And then you just evaluate. Right? So this is the double integral over d. of 2xy plus 2xy plus 1 minus x squared minus y squared dx dy dA. Double integral over the disk of radius 1, and this is x squared plus y squared less than equal to 1, 2x4xy plus 1 minus x squared minus y squared. How would you do this integral? How would you do this integral? What's a sort of obvious move to make for this guy, right? You're integrating on the circle, right? X, y. Circle of radius. You're integrating on the circle of radius 1. Right? And you're integrating this sort of thing. What do you think would be a good move to make here?
Convert to polar.
Convert to polar, yeah. So you say, okay, I'm going to integrate r d theta, right? This becomes 4 r squared sine theta cosine theta plus 1 minus r squared r squared r dr theta. Where theta goes from 0 to 2 pi, and r goes from 0 to 1. Right. And then you'd integrate that. It's not so hard. It turns out to be pi over 2. So that would be the flux of the field through the surface. Okay. Okay. So yeah, I mean, it's I don't think there's anything too hard here. It's just remembering what things mean, right? If somebody says, I'm going to integrate this field over the surface, you say, okay, what does that mean? It means I'm going to take the integral of the field dot the normal vector on the surface, right? Which means I'm going to take the field dot the normal vector against the magnitude of RU cross RV, et cetera, et cetera. So you just have to keep things straight, and then after that, it's just calculation. Okay, so it's not hard. You just have to remember what things are. It's in some sense, this last part is a lot of just memorization. Okay, so in the last minutes, I'll let you set up one integral. So S is the hemisphere x squared plus y squared plus z squared equals 1. Where y is bigger than 0. Right? So this is the upper half of the unit sphere. And you're going to take the outward normal. And the field f of x, y, z is going to be negative 3z squared, negative 3x, comma, negative 3x squared, comma, negative 3y squared. Oops, the picture is wrong, sorry. That would be with z bigger than 0. I actually want y bigger than 0. Right, so we're taking the other half of the sphere. When we're chopping it this way, we're taking the part on the other side. just take a minute and see if you can figure out how you want to parameterize and get the normal vector. Okay. We're kind of running out of time, so here's one idea. Right? You could do it like this. R of xz is x 1 minus x squared minus y squared minus c squared to the half, comma c. Right? Where x squared plus z squared is less than or equal to 1. Right? So you take this is your domain, right? The x in the xz plane. This thing is x squared plus z squared less than 1 is your domain. And then right, you have x, z, and the y. This is the y. Okay. And then you would get you take r sub x and r sub z. You get 1 negative x, 1 minus x squared minus z squared to the half, comma 0. Right. R sub z is going to be 0, negative z, 1 plus x squared minus z squared to the half, comma 1. And then you go from there. So maybe the hard part is figuring out a useful parameterization.
Would it still work if you used y? Like, if you...
So you could, right? But you see, then your domain would be like this, right? This would be your domain, and you'd probably have to do it in 2 parts, right? You'd have to do this upper. You'd have to do the upper quarter sphere, and then this lower quarter sphere also. Yeah, but that would be fine. Okay, that's it. Thanks for coming today. I know it's